All right, if you survived the intro, you deserve this special treat. Today, I'm going to show you that we are in a black hole. The way I'm going to do that is using this metric, using some math. This is called the Schwarzschild radius. The Schwarzschild radius, also known as the Schwarzschild metric, and the Schwarzschild solution does, is it allows you to figure out the radius of an event horizon for a black hole given its mass. Or conversely, you can figure out, if you know the mass, what the event horizon would be if you could compress that mass into a volume below the event horizon. Maybe that makes sense. You can read more about it. Well-established equation, I didn't make it up. All right, so this is it written out. The terms here are is the radius of the event horizon of the black hole. 2, G stands for the gravitational constant, which I've written out here. C is the speed of light, which I've written out here. M is the mass in question. So there's only 2 unknowns in this. R, the radius of the black hole, and M, the mass of the object you're talking about. So we can plug in a mass, if we know the mass, and solve for the radius, or we can plug in a radius and solve for the mass of the black hole. All of the constant values I found, I got off Wikipedia, but you can choose your source. It's not going to change the end result. Okay, so these are quantities I got off the internet. Mass of the observable universe, radius of the observable universe, in kilograms and meters, very large numbers. So what I'd like to do is plug in to this Schwarzschild solution the radius of the observable universe, which has been calculated, estimated. Plug that in, and if we plug that in, we're able to solve for M, for what should be the mass of a black hole with a radius equal to the radius of the observable universe. That's the key statement. All right, so I'm rearranging because we're going to solve for M. So we started with R, and we just divide, multiply to rearrange to solve for M. So to find the mass at the center of your black hole with a radius that's known, speed of light and gravitational constant also known. So we receive this equation. Then we take the known that I gave you before, the radius of the observable universe, and we're going to plug that in for R. Okay, so what we're doing is solving for M, which gives us a black hole with an event horizon. Well, you can read it. So the mass, and I plugged in the known quantities here, so the radius of the observable universe, this is speed of light squared, 2 times the gravitational constant. And you can see here right away that the units, which I've written out here, are going to cancel out to give you the units you desire. So we have meters cubed, meters squared. So these will cross, give you 1 meter down here. We've got the meter there, so meters cross out. They're no longer in our answer. You can see kilograms down here and seconds squared. So seconds squared are going to cross out. Kilograms, it's divided by kilograms down here, which means it's going to flip over here to the solution. So mass is going to be in kilograms. Perfect. So use a calculator, solve this equation. And, well, we find out that we fall a little bit short. the question was, what mass does it take to create a black hole with an event horizon equal to the observable universe? The mass required for that is 2.98, so essentially 3 times 10 to the 53rd kilograms. The estimated mass of baryonic, which is ordinary non-dark matter in the observable universe, is 1.5 times 10 to the 53rd kilograms. So the Schwarzschild solution suggests that we don't have enough mass to create a black hole with a radius of the observable universe. But here's the kicker. The estimated baryonic mass, so this is non-dark matter. I've got a wild card to play. And it's dark matter. I say it in a funny voice, but it's very true. Dark matter is estimated to be 5 times in terms of its influence on the gravitational field, so essentially the way they think about it in terms of mass. 5 times the mass of ordinary matter. Now, if you multiply 5 times the estimated mass of baryonic matter, you're off the charts in terms of where you need to be for this. So, you don't even need 5 times the dark matter to cause an event horizon to form at our observable universe radius. That's it. In the next video, I will talk to you about another concept, the quantized universe. We live in a quantum reality where infinities and zeros, neither of them really exist. And I'm going to use that concept and expand it to give you a frame to think about a quantized universe. Thanks.